So, Bobby, we talked about the air core.
Since air core, that there was no core so far.
Yes.
Lossless air. So only mu zero was there. Yes. No mu r in between in oil.
And we realized that if we want to increase the sensitivity of the coil, the best thing to do is to generally, right, is to increase the size of the coil.
The size and the number of turns, that is what.
Size and number of turns, yes. But then, let's say you have
Size imitation.
yes, an application where you have to somehow miniaturize the surge coil. In that case, I mean, you'll be hard pressed to have lots of turns.
Correct.
Is there something else we can do?
Then the resistance will also go up.
That's not going to help at all.
Yeah.
Right? So, does that mean that we cannot do surge coil? Is there something else we can do?
Oh, so you have the solution.
So, what if I say we put something in between these coils? Before it was the air core.
Like ferromagnetic material.
Yes. Let's say to increase the sensitivity, we have a cylindrical core.
Okay. It's a soft magnetic material.
Yes. And that's made of a, soft ferromagnetic material.
Which allows some high relative permeability.
Yes. Which means your relative permeability mu r can be anything between, let's say, I don't know, let's say 200 to 20,000. You said 1 lakh.
Yeah, it's also available 1 lakh.
Let's make it 1 lakh. So a large range.
Yeah.
But how does this improve or increase the sensitivity? Because now we had before V equals mu 0 N A dH over dt, right? But now we are introducing this mu r in the equation. Now all of a sudden, you're increasing this
So with the multiplication part.
with the multiplication factor here. A really big multiplication factor without even touching the size of the coil.
Yeah.
So, nice way of increasing the sensitivity. But as we know, nothing is perfect, right?
Yeah.
So, so mu r, I think, I'm not sure if we explained, we did in the first class, is basically the permeability of your core, right, divided by
Permeability of air.
of air. Now, this is an ideal situation. You're actually multiplying your, but in reality, this cylindrical core made of your soft ferromagnetic material, now we said, is actually dependent on your relative permeability 1 plus n. Now I'm sure you've seen this equation before somewhere. Now,
What is 1 plus n? Mu or minus 1?
yes,
What
so
n?
the key factor, I mean, we know everything else here, right?
Yeah.
Mu c is your actual permeability of the core, right? Because before we thought it was mu r, but in reality, there's something called n. That is
Not number of turns.
It's not the number of
Just for n.
yes. Okay. Actually, we switched between small and big. But let's say, okay, just to make
I
this,
think you are consistent. It's small n.
was I?
It's not.
Because there are so many variables that has the same symbol. Well, I'm using the same symbol. Well, we can make this, let's say ND. Okay. Now I'm giving you a hint here. So this ND is what we called a demagnetizing factor. Okay. So that depends on the geometry of the core. So what does it really mean, demagnetizing factor? Let's say you have a sphere in mind. Let's say this is, in 3D. Okay? And let's say you have an ellipsoid. Okay? Now, both are, let's say, made of a so let's say both are made of some ferromagnetic material. Now, what happens when you apply a magnetic field? Let's say you apply a magnetic field. What's going to happen is the field is going to converge, right? Assuming this is, much larger than 1. Okay? And then from the outside, it's going to come out like this. So the field as like is kind of going to move towards that.
So before that, it was a uniform field.
Yes. Now, if you put something like this, right?
Modifies the existing field.
Exactly. Right? Now, similarly, if you expose, let's say, an ellipsoid, you get, again, field inside the ellipsoid, where the fields kind of converge in. So, this demagnetizing factor, ND, depends on the shape.
Okay.
Right? Shape of the pole, or shape of the material that we put in between this coil.
Okay.
So, and interestingly, so if you have, now students can, there's a nice little paper here. Students can read more about demagnetizing factor.
Okay.
But this is something we cannot avoid.
Okay.
When we introduce a core. And obviously, your actual or apparent magnetic permeability is dependent on your demagnetizing factor. Now, if you have something like this, let's say just a simple cylinder, right? And you can refer to this paper for these numbers. N is 0.41.
Okay.
Okay? If you go this way, N is 0.18.
For
right?
the same.
Same. If you just move it around and then if you explore the same magnetic field.
Okay.
Right? So
magnetic field is still in this direction.
Yes, the magnetic field is in this direction. But your demagnetizing factor goes from 0.41, 0.18. Now, this is something really interesting because if you expose both to the same magnetic field, you end up getting two different demagnetizing factors. Now, one of the reasons, right, could be if you have, let's say, a core in this direction, and let's say you have
and the field is also in that direction.
Let's say a field is in this direction.
Opposite, 90 degree.
Yeah. Okay. Then, imagine this has some sort of little magnets inside. Then, you are going to arrange that this south, north. Now,
what are those magnets inside?
Those are just little dipoles, let's say.
Okay.
Inside. That are moving coordinate displacement.
Okay.
Similarly, what happens if you now, because it's a hard concept to grasp. If you think about it, why does this change this value? And that's obviously a critical value because it's related to mu c.
Yeah.
And then mu c is related to your voltage output. Similarly, if you apply,
so here you are saying the opposition is more.
Yes, you get the point. So here, when the poles are closer, right? Now another example: north, south. When the poles are closer, the demagnetization field of this is strong. Okay, which is why you have a higher demagnetizing factor.
Hmm.
But here, that demagnetizing factor, because these poles are further apart, right? And you're still trying to now apply magnetic field this way. This is further apart. So this demagnetization factor is much smaller.
So what is the ideal value for ND? 0?
Well, if you put, yeah, like if you put 0, then you get your mu r. But actually, it can be 0. No? There's a case in the ideal. Can n be 0? I'm not sure.
Or it can be very
Or
close.
very, very small. So the whole idea is you want this n to be small as possible, right? Now, for our case, right, we assume an ellipsoid.
Mhm.
Now, for such a case, again, you can find these equations in textbooks. In our case, this n is equal to d I squared divided by LC squared, natural log 2 LC DC. Now, you might be wondering, sorry, what is this DL and this one is. So here, this is a cross section, right, of this. Now, this is your coil, this is your core, this DI is your inner diameter of your core, D is the outer. Right?
Cross section of a similar, not same.
Not the same, not the same.
Otherwise, because that has only one layer of winding.
Yes.
Here,
Yes, exactly. Yeah, not exactly this, but yeah. But key point here is you can see this is much larger.
Yeah.
Longer.
In coil.
Longer, right, than the actual coil.
Hmm.
Now, there's a reason for it. If you look at this equation, what do you see? You said we need a small end. What do you have to do to get a small end?
ND.
ND. Stick to that. Stick to convention. Yeah.
Equal to D square, is it? Capital D is
DI, sorry.
DI. That's the inner diameter.
Diameter of the core. Well, diameter of the core.
Okay.
Yeah. Okay. What would be
So we
the
want-
ideal core?
Yeah, we want
case.
ND to be very low
want
as possible. That means
D to
LC has to be, is it LC?
Yes, LC.
LC has to be very large compared to DI.
Yes.
Okay.
So ideally, you're looking for something a thin, long core to maximize your mu c.
Okay.
Because then ND will be small.
Hmm.
Okay. Now, this is just a graph showing the aspect ratio, right? So here we have your LC over DI, which we talked about before. Here's your mu c, right? Here you have DI, LC.
What is x-axis?
Oh, 2 LC over DI, which is
That component. That
this.
okay.
Okay. Four different relative permeabilities. What do you see here? See this here. This is for 10 to the power 2. Curve is getting
to a constant value.
to a constant. Why is that?
That is ND, y-axis.
Y-axis is the mu c.
Mu c. Oh, okay.
And this is your 2LC.
Mm-hmm. Mu r
Is increasing.
Okay. So the material, I mean the mu r of the material is for the bottommost one 10 power 2.
And this is 10 to the power 5.
Okay. So for low values of 2 LC by DI,
Yes. This is
the ND is affecting.
yes.
Hmm?
Yeah. Exactly.
Higher values, we are almost close to the mu r itself. The mu c is almost close to the mu r itself.
Correct. But then what happens when you increase the probability? It's becoming what?
Yeah, you are getting mu c equal to mu r for a larger ratio of 2LC by DI.
Yes, because for large, if you go back to this one, right? For large mu r, right? This one component goes away, right? So it's becoming closer and closer to 1 over n. So your mu c then totally basically depends on 1 upon n.
ND.
ND. ND. Sorry, ND. D. So if you have very large permeability, right, your mu c co is totally dependent on this demagnetizing factor we talked about before, of very large values. So what does that mean? That means that for very long course, right, and high permeability, right, we are not really depending on mu r, the relative permeability. We are depending on just the demagnetizing factor.
But it has happened due to the high mu r, no?
Yes. Yeah. That's true. That's true. Yeah. It happened because we chose a very high mu r value.
Yeah.
Then it depends.
Otherwise, this will not happen.
Yeah. For lower values, yeah, it's more dependent then on this, right?
That dimension.
Okay. So everything's good. We have now another demagnetizing factor we need to consider.
One more.
No. That last one we talked about. Okay. But this high output
Is still inspiring because its output is,
yes,
the gain is very large.
yes, right. So we still have high output, right? But we are sacrificing something compared to an air core coil. What is that?
What is that?
By introducing this core, you are most probably sacrificing the linearity.
The core is not that friendly. It's not a linear component.
For many reasons, right? So if you think about the core, here, right? So it can be normally made from the best materials, but there are some non-linear factors that affect this. What is the most common one, you think? When you talk about a core with a certain relative permeability, is that it saturates?
Yeah, the hysteresis.
Yes. So one is hysteresis. Right? So that introduces some nonlinearity. Temperature?
Yeah, I think temperature affects this permeability of the material.
Yes. I don't have an equation for them, but it does.
Yeah. Also, the permeability of the material changes with respect to frequency, I think.
Frequency is another one. And I'm sure there are some other magnetic noises.
Yeah.
Right, let's just say other magnetic noise. So there are some things we need to consider again. So you cannot just simply put in a core and multiply your voltage output. Now, there are a couple of papers here, and they've done a lot of experiments on air coils and cores. So we derived the voltage output for an air core before. So we're not going to do this again. But so these equations are from these papers.
Okay.
So few things we need to talk about before we write this equation. Now we know mu c is mu r 1 plus nd mu r minus 1. That's 1. Okay. And we also know that m is equal to di squared divided by lc squared id. That's something not particular. Natural log 2lc divided by d
2SC divided by DI.
minus 1. We know these things we talked about. Now, they also found out the ideal inner diameter is approximately 0.3 times the D by experimentation
For good ND.
for good ND. Okay, so 30% of this is the ideal value for this.
Okay.
Okay. They also found that L is ideally between 0.7 to 0.9 LC. Okay. Again, by experimentation. The students can obviously have a look at this paper.
LC is the
LC is the length of the core.
length of the core, yes. And small l is the length of the coil.
Coil.
So it's 0.7.
to 0.9.
Okay, okay.
So,
So is there a bracket for that? 0.7 to 0.9?
you mean bracket means?
LC is common to.
Oh, yeah. So,
Oh.
yeah, exactly. So, oh, yeah. Okay, let's say LC, right? Yeah. So, in something in between. Now, if we put all these things into an equation, into the original equation we have with zero mu r, we get something along the lines of 0.9 10 to the minus 5 f L cube d squared di 1 over natural log 2 L divided by di minus 1 times h. So, it seems that voltage is directly proportional to cube of the length. It seems that length plays a key part when you design a coil with a ferromagnetic or ferromagnetic core. Also,
The number of turns is not there in this equation.
the number of turns have disappeared. Yes.
Okay. So probably it is captured in that L cube. Is it
Here.
the length of the core or length of the coil?
This one is the length of the
Coil.
coil.
Yeah. Coil. Because probably in that the number of turns is
Right.
captured. Yeah.
Because this here, right?
Yeah.
It's nothing to do with the
Core. Yeah.
and we also have the diameter of the wire. Right?
Yes.
So yeah, you're right. Yeah, I think this is exactly where it's
Yes.
captured.
Yeah.
So also the all important signal to noise ratio again, and we know that is V. This one, let's say, divided by VT. VT is your
Noise.
noise, right? Is 1.4 times 10 to the 8. Now this is your bandwidth. Sure, long. Running out of space. Natural log 2 L di minus 1. Okay. Times h. Again, but what I want to show you with these equations is that, again, if you look at the signal noise ratio, right? Again, this L pops up, right? So it seems that the L is a key value that we would consider if you're talking about a
High SNR.
yes ISNR for
Delta F is the bandwidth, is it?
band. So frequency also plays a part in that, right? And I think you talked about them before, how frequency affects the output of the signal. Yeah, so that's
So these are taken from this reference.
Yes. Okay. In fact, if you see all the slides, references are given for each and every slide. So students who are interested can, access those papers online and read more about anything that they're not clear about. So Bobby, we one of the things that we talked about was the output, right? Which is a derivative, for air cores and also for
Because the induced voltage itself is based on this Farad law.
Right? Which talked about when we started these electromagnetic sensors. So one of the things that people normally use is what we call an integrating amplifier.
Okay, so from the voltage, you want to get back the flux density.
Yes.
So you integrate.
Yes.
Okay.
Right. So I'm sure the students have again studied this.
Yeah, it's an electronic integrator.
Electronic integrator.
Yes.
Yes. This output here. Now you have a capacity in the feedback loop, right? So the output signal depends on how long the length of the time the voltage is present, right?
Yeah.
Input. As the current through the loop charges and discharges the capacity. Okay. Now that's straightforward. Then you also have this offset.
Yeah.
Why would we need that in this case? We talked before about zero drift, and if your output is somehow drift,
maybe to take care of some of the op-amp non-idealities.
Yes. So you can actually tweak the offset here, right? So that you can take care of any kind of non-idealities in you experience from this integrating amplifier. Here, why do we need this one? Or rather this one?
Yeah, again, I mean, ideally a capacitor is enough, but the bias current of the op-amp, etc., we charge this capacitor and drive into saturation.
Yes.
So you need some discharge path for that.
Which is why you have.
Yeah.
So
all practical integrators, we have this resistor in parallel, which will be a large value, right? Compared to the reactance offered by C for the frequency that we are interested, right? So that it's predominantly, output is decided by the C.
Yes.
While for the bias current, the R. Yes. So
there.
What? Yes.
Yeah. So I thought I'll just include this figure
What is
here.
this very nice diagram?
Yeah, it's a very nice diagram because it kind of is related to what we're going to talk about next, some applications. So, you have your coil. I mean, doesn't have to be air core. It can be the ferromagnetic core. And we talked about the amplifier, connected to the amplifier. We talked about the noise characteristics. Then, if you want to connect it to an SD card or microcontroller or something like that, enable an ADC. Now, generally, when you go out and buy a search coil, let's say, you just want to see a value, right? If you want to show a search coil, you measure a magnetic field, you just want to see a value. So in this case, you would have a flow diagram or different modules like this connected. So which is a blue diagram.
So if you want to record for a duration, this may be better.
Yes. And it's related because later on we'll talk about some applications, and then most of these applications, they use this kind of diagram to measure the magnetic field over that period of time. So now let's say you designed a search coil. How would you know if your search coil is accurate? What do you have to do for that?
I will have to maybe measure some known magnetic field.
Yeah.
Something which I know already.
Maybe a range of
Yeah.
to see how accurate your measurements are. So this is something explained more in this paper here.
Okay.
But basically, they have your you have your sensor here, which is your search coil.
Okay. What is that bigger tube?
Yeah. So this bigger tube, we also talked about this at the beginning of search coil lecture, which is a solenoid,
Mm-hmm.
right? So solenoid,
It's also a coil.
it's also a coil, but it produces, if you give a current, it produces.
Oh, you are sending current through that.
Yes. Right. So
And
you have a
when-
function generator here,
Okay.
right? That is connected to this solenoid.
And then you are producing an magnetic field.
Yes, you're producing a uniform magnetic field,
Mm-hmm.
say B, right? And your sensor now search.
You are putting it side and see whether this gives you what you are producing.
Correct.
Got it. Got it.
Right. So a function generator will give you your changing current to this. You have a change in magnetic field, which is then detected by the sensor. Okay. But here they have a couple of. So here what they're doing is they've tested for different frequencies, right? With a preamplifier and without a preamplifier, right? And kind of analyze the results. Now, in this case, you also have magnetic shielding, so that that
External magnetic field doesn't
will not affect the results. Now, they also
That's to avoid the interference.
yes, any kind of electromagnetic interference. Right? Now, if you also have, let's say, in this, so here you have a magnetic field, right? But here they also tested the sensor without a magnetic field to analyze the noise. There's any kind of noise, and so same magnetic shielding case, it's still inside the solenoid, but there's no magnetic field. So different ways you can calibrate your sensor, right, to see if it's working according to your design principles.
Okay, so the bottom one, since there is no excitation given to the outer coil,
Yes.
there is no magnetic field. You may have still some output. That is due to the new noise.
Hopefully not, but
Yeah,
in reality, yes,
Yeah.
I'm pretty sure there will be some output
correct.
here.
So it is due to the noise from the coil preamplifier. What else we had?
We had the
Yeah.
Right.
No. The blockwise. We had the sensor coil, preamplifier in the previous slide, and then unload to digital converter. That will also introduce some noise.
yeah, this one.
Oh, that is there somewhere. Okay.
Yeah. So all these things. Here we have some noise.
Yeah.
Okay, here and here. So you'll be able to analyze that noise, and then hopefully you might be able to maybe there's an offset or there's I don't know.
Now, but anyway, some quantity smaller than this you cannot resolve.
Yes. If it's there, then yeah, that's right. So then it comes back to what? Resolution.
Correct.
Right.